Okay, in this video I want to talk briefly about horizontal asymptotes. These are limits at infinity of rational functions. So in general, these have the form a naught x to the n plus a1 x to the n minus 1 plus dot 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 all the way down to an, and then over another polynomial b naught x to the m b1 x to the n minus 1. So this is just a very general form for something that looks like this. So an example of this would be, let's say, 5x cubed plus 4x plus 3 over 7x to the 8th plus 2x squared plus x plus 1. So this guy here is the general form of this. So in this case, my a naught would be this guy, and my b naught would be this guy. It's the coefficient on the highest exponent x. Okay, and so what I'm saying is that if we take the limit as x goes to infinity of this rational function, which is the quotient of two polynomials, polynomials being these guys, right? They're being divided, so it's a quotient. If the degree in the numerator, if the highest degree in the numerator is higher than the highest degree in the denominator, then the limit, which is L, the limit as x goes to infinity of this guy, will be infinity. And it does not exist, right? Because it's infinity. Why? So the way I think about this is if the degree in the numerator is higher, it's top heavy, right? So if I have something like a over b, if a is much larger than, let's say a grows much faster than b can't weigh it down enough to stop it from growing. So it just keeps growing without bound and growing and growing and growing and growing until we go off to infinity. So I think of this as being top heavy, right? The degree n is larger than the degree m. So an example of this might be like x squared plus 3x plus 1 over x minus 2. X squared grows much faster than x, right? We're looking at the difference between this and this, right? X squared grows much faster. So this is going to go off to infinity, okay? Now if n is less than m, L, the limit as x goes to infinity of all of this, is going to be 0, right? And the way I think about that is it's bottom heavy. So if I have, let's say, a over b, if b grows much faster than a, well, a can try and grow, but b is just going to keep weighing it down. And it's going to look like this kind of, think about 1 over x, right? X is growing much faster than 1, obviously, because 1 just stays the same, so it's going to approach 0. It'll never go negative because there's no way to make it negative if we're going out to positive infinity. So it's just gonna bottom out to 0. So our limit as x goes to infinity is going to be 0. And if n equals m, so if the degree in the numerator equals the degree in the denominator, then we take the ratio of the leading coefficients, we say, or the coefficients on the highest degree x. So in this case it would be 5 because it's on x to the third, which is the highest power, and 7, which is on x to the 8th, which is the highest power in the denominator. So L is going to be a naught over b naught, where a naught and b naught are the leading coefficients, the coefficients on the highest degree x's. Okay, so let's look at some examples. So the limit as x goes to infinity of 3x squared plus 5x minus 1 over 2x plus 3. So I'm looking at the degrees here. This guy is 2, this guy is 1, so it's top heavy. So this guy does not exist, right? Because it's going to go to infinity. It's top heavy, so it goes to infinity, just like we were talking about earlier. Okay, let's look at this guy. So 7 is my degree in the numerator, 7 is my degree in the denominator. Right, we're taking the limit as x goes to infinity. Very important that we note that we're taking x goes to infinity and not x going to a finite number. Right? This isn't the same for x equals 0 or x equals 3 or x equals pi or whatever. It has to be x equals infinity. I notice that 7 is 7, so these are matching, so m equals n, and we take the ratio of the leading coefficients here, right? So what are my leading coefficients? Well, my leading coefficients are going to be 5 and negative 3. So this limit is equal to negative 5/3. Okay, moving on, I have the square root of 12x minus 1 over 3 halves, x to the 3 halves minus 2x plus 1. Okay, this is a little bit more tricky to think about, but if we think about the kind of, I'll put it this way. I think the good way to think about this is these are not equal, because these are not the same. But we can kind of think as if we're looking at this, the square root of 12x. Yeah, the square root of 12x minus the square root of 1 over x to the 3 halves minus 2x plus 1. So we're thinking as if this is going on. Now, this is the same as the square root of 12 times x to the 1/2, right? Because the square root of x, we're talking about the square root of x here, is the same as x to the 1/2. Okay, so I have the square root of x, whatever comes after this, it doesn't matter. And then x to the 3 halves is in the denominator. 3 halves is clearly larger than 1/2, so this is bottom heavy, so this will go to 0. So this limit is equal to 0. Okay, so if you see a square root over everything, they're not equal, but you can think about taking the square root and splitting it up across the sum. That doesn't actually happen, you can never actually do that, but we can think about it this way, okay? Just to give us an idea of what's going on, okay? Next we have the limit as x goes to infinity of sine x. Okay, well, if you are a little bit more mature in your mathematics, you understand that sine is actually an infinite polynomial, but it is not a rational polynomial. It is not a rational function. All of that is a bunch of nonsense if you're taking Cal 1 for the first time, but my idea here is we want to see if sine x has a limit as x goes to infinity. Let's think about what sine x looks like to see if we can get an idea of what that limit might be. Okay? Sine x looks something like this. It oscillates between -1 and +1. So at its lowest it's -1 and at its highest it's +1, and it just keeps oscillating forever. So as I keep going out towards infinity, it keeps oscillating, and it never settles on a value. It just keeps oscillating regularly. If we can't find a value that it settles to, and what I mean by that is if you think about excuse me. And what I mean by that is if we look at our other, think about 1 over x, right? It has a limit as x goes to infinity, namely 0, right? Because it gets closer and closer and closer to 0 as we go out to infinity. In other words, it kind of settles to 0 as we move out towards infinity. But sine x never quite settles. Sine x never quite settles. So we can't find any particular value that sine will go to as x goes to infinity. So we say that the limit as x goes to infinity of sine x does not exist. Similarly, the limit as x goes to infinity of cosine of x does not exist. You can also find that the limit of tangent, cosecant, cotangent, and so on as x goes to infinity also don't exist, because they're all periodic and oscillating in some way or another. So trig functions do not have limits as x goes to infinity on their own. Compositions of them may, but on their own they do not. Okay, that kind of wraps up what I wanted to say about horizontal asymptotes and limits at infinity. If you found this video helpful, please consider liking and subscribing. Thanks.